the coming section, which is heat and thermodynamics in general. And the first section within heat and thermodynamics we'll be discussing about today will be about thermal expansion. But before that, we will discuss a few general things. Yeah, Ruzba, I will send you the module to later. Okay. So the first thing we will discuss about in this section is the concept of heat itself. So heat is a form of energy which is associated with the molecular kinetic energy. So kinetic energy of the molecules of any substance. That form of energy is called the heat energy. So for solids, for example, it is the vibrational kinetic energy of the constituents molecules. For fluids, that is for liquids and gases, it is a combination of vibrational, translational, and rotational. And to that end, the temperature is a parameter that we use to understand the average kinetic energy of molecules. So temperature is, I mean, traditionally we define it as the degree of hotness or coldness, such that heat as a form of energy always flows from a region of higher temperature to a region of lower temperature. But in proper thermodynamics, we will see that the more technical definition of temperature will come on the basis of absolute temperature, which is associated with the average kinetic energy of the molecules of the material whose temperature we are measuring. That will be like the thermodynamics definition of temperature. So even though, solid materials don't look like they are in motion, but at the molecular level, the molecules of a solid material are also in motion, although they cannot really move about in such a way that the mean position of the molecules is moving. They can only vibrate with respect to their bond lengths, or you can visualize the intermolecular bonds between solid molecules like tiny springs. So the molecules can vibrate with respect to those bonds, okay, or vibrate about those bond lengths, but they can't really translate or rotate about like that. So that's why a solid has the property of fixed volume, a fixed shape, a fixed density, etc. Whereas fluids, which includes liquids and gases, has a more a structure where the volume may not be fixed in the case of gases, or at least the shape is not fixed in the case of a liquid, even though the volume might be fixed, because the molecules are not so strongly attached by intermolecular bonds. So they can not only vibrate, but they can also actually move about, and they can move about in such a way that they're both rotating and translating. So liquid molecules or gaseous molecules can store kinetic energy on the basis of vibrational kinetic energy or translational or even rotational kinetic energy. Whereas when we talk about the molecular level kinetic energy of solids, it is only the vibrational kinetic energy. The solid molecules can't really move about like fluid molecules can. Okay? So heat is that form of energy which is the cumulative kinetic energy of the constituent molecules of a given material. Translation means non-rotational motion. The translational you have understood in kinematics. It means that if a body is moving such that there is no rotation happening about any axis, so every particle within that body has the same identical displacement, identical velocity, etc., then we call the motion as translation. Whereas, for example, if a body is moving in such a way that it is rotating about a fixed axis, like when you open a door, the type of motion that the rigid body of the door does, or a fan that is rotating about a fixed axle. So those are called pure rotations. Whereas there can also be a type of motion where there's combination of rotation and translation, like the rolling of a cylinder on a horizontal surface or down an inclined plane. So such a motion, like a rolling motion of a cylindrical body or a spherical body, that represents a combination of rotation and translation. Yeah, translation, beta, you will get the explanation of translation in any text of kinematics. No? Translation of a rigid body is a motion such that there is no rotation. Okay. So the translational motion of a rigid body is one where there is no rotation involved. Therefore, every particle within the rigid body has identical displacement, velocity, and acceleration. That is the example of translation. Like a block sliding down an inclined plane, okay, that is an example of translation. But a cylindrical body or a spherical body rolling down an inclined plane, that is not translation, because it is both rotating as well as moving linearly. So that is the difference between these. Okay. So as I was telling you, in terms of thermodynamics, the more appropriate definition of temperature is that the temperature, when expressed in what is called the absolute scale, absolute or Kelvin scale, okay, is a parameter directly proportional to the average kinetic energy of a molecule of the given material. Okay. So that is why actually heat as a form of energy flows from a region of higher temperature to a region of lower temperature, because the molecules in a region of higher temperature are basically moving with more kinetic energy. Whether they are vibrating or translating or rotating or a combination of all these things, they have more kinetic energy compared to the molecules in a region having lower temperature. So when such molecules which are having higher temperature versus others which are having lower temperature come in contact, then always energy will be transferred from the ones which are having more kinetic energy to the ones which are having lower kinetic energy. So that is why heat as a form of energy transfers from higher temperature to lower temperature till thermodynamic equilibrium is established. In fact, that is called the zeroth law of thermodynamics. Okay. So we can write that down also here also. Zeroth law of thermodynamics is that when two bodies or two materials which are at different temperatures are brought in contact, thermal contact with each other. Thermal contact means heat can flow from one to the other. Then heat always flows from the higher temperature body to the lower temperature body until what happens? Thermodynamic equilibrium is established. And in thermodynamic equilibrium, the temperature of both the bodies or materials will be equal. So when two bodies of materials at different temperatures are brought in thermal contact, then heat as a form of energy will flow from higher to lower temperature until thermal equilibrium is established. Okay. So this thermal equilibrium means same temperature. Or uniform temperature throughout is established. Okay. Now, how heat flows, that's another matter. Heat can flow. Yeah, the reason is this only, no, that higher temperature material has molecules with more kinetic energy. Lower temperature materials have molecules with lesser kinetic energy. So if there is some method by which kinetic energy can transfer from one material to the other, always the energy will flow from higher energy bodies to lower energy bodies till the energies equalize, till the average kinetic energy is equalized. Okay. Or you can just treat this like an experimental fact also at this stage, Sarvesh. If it is confusing, just treat it like an experimental fact, because these laws are basically based on experiment. That when we bring bodies, so if for example, you put an ice cube into a cup of normal water at room temperature, the water's temperature will lower and the ice will eventually melt. It's not that the ice will get cooler and the water will get hotter. अरे equilibrium में same temperature होता है बेटा. Heat will flow until what happens? The temperatures become equal. When two bodies which are initially at different temperatures, now when they are brought in contact, what happens? Heat will flow from one body to another until what happens? Thermal equilibrium is established. So you brought one body in contact with another one. This is initially having T1, this is having T2, where suppose T1 is greater than T2. So heat will flow from one to the other. This is the direction in which heat flows. Until what happens? At some stage, heat will stop flowing. Na? So that will happen when the two temperatures become equal. So there is thermal equilibrium. You must have done some basics of this in 9th, 10th also. Yeah? It's not that difficult. For example, specific heat capacity concept and all that. So thermal equilibrium means same temperature. Two bodies are in thermal equilibrium when they have same temperature. Okay. So in order to understand all these things about thermodynamics better, first of all, we will talk about the different scales of temperature. Okay, then we'll understand few more properties. So temperature scales. As you know, the standard international unit of temperature is Kelvin, and that scale is the Kelvin scale, also called the absolute scale for temperature. So in this scale, the temperature of boiling point of water, okay, obviously at STP, standard temperature and pressure, that is 373 Kelvin. At 1 atmosphere pressure, the boiling point of water, okay, I'll take you back later. Okay, and the melting point of ice under standard atmospheric pressure is 273 Kelvin. Okay, and in this scale, importantly, 0 Kelvin is called the absolute zero. It is a theoretical temperature. It is theoretically the temperature at which molecular kinetic energy ceases or molecular motion ceases. Okay, so this has not been achieved in a physics laboratory yet. Okay, the 0 Kelvin state, which is theoretically called the absolute zero, it is not yet achieved. Okay, in laboratory conditions or practically. In physics laboratories, extremely low temperatures going up to about, you know, 0 point something Kelvin, 0.2 Kelvin, 0.3 Kelvins have been achieved, but 0 Kelvin is not achieved, and it is still a matter of, you know, debate in physics whether it can exist or not, because for molecules to not have any motion at all, okay, there are some theoretical discrepancies over there. So anyway, at our level, we need not concern ourselves with that. We will be mostly dealing with much more simple situation, everyday kind of situations, where the temperatures are much, much higher than the absolute zero. Okay. So that is the first scale of temperature. Then the second one, which is most commonly used, is the centigrade or Celsius scale. So in that, the boiling point of water is 100 degrees Celsius or 100 degrees centigrade, as you know, and the melting point of ice is, as you know, 0 degrees C. Okay, so we can also understand that a temperature difference of 1 degree C is equivalent to 1 Kelvin. Okay, because but because the interval between melting point of ice and boiling point of water is divided into 100 equal divisions in both the Celsius scale and the Kelvin scale. Okay, because in both scales, the temperature difference between boiling point and melting point are 100 equal divisions. Okay. But the scale is such that 273 Kelvin, a temperature of 273 Kelvin equals to a temperature of 0 degrees C. A temperature of 373 Kelvins equals to a temperature of 100 degrees C. So therefore, X degrees C will become 273 plus X Kelvin, or Y Kelvins will be equal to Y minus 273 degrees. So this is the conversion of centigrade or Celsius to Kelvin. Just make a note of this. I will take you to the previous slide also, those who have not written down. But first, write down this thing. So the conversion of Celsius to Kelvin or vice versa is very easy, because it's just that the values are different for melting point and boiling point, but the division of one, or the division of the temperature range between the two, is equal for both. 100 divisions of centigrade equals to 100 divisions of Kelvin. Above the conversion, in both scales, the temperature difference between boiling point and melting point of water, that is, are 100 equal divisions. Okay, I'll just take you to the previous section of zeroth law once more. Yeah, that is Krupa. That's correct. That's another way of expressing the zeroth law of thermodynamics. That if two systems are in thermal equilibrium with a third one, then any of two. It's like, if A is in thermal equilibrium with B and B is in equilibrium with C, that means A is also in equilibrium with C, because the meaning of thermal equilibrium is that the temperatures are equal. Okay, so the statement, Krupa, that you are giving now of the that's another form of the statement of zeroth law. So it is like this. It's like this, that if one body A is in thermal equilibrium with another body B, okay, and A is also in equilibrium with C, then automatically it means that C must be in equilibrium with B. So basically, if A is in equilibrium with B, it means that temperature of A is equal to temperature of B. Okay, and B is in equilibrium with C. That means temperature of B must be equal to temperature of C. So this automatically implies that A's temperature is equal to C's temperature, which means they are in thermal equilibrium. Okay, so that is a sort of more theoretical way of expressing zeroth law of thermodynamics. But whereas when we apply it practically in problems later, we will see that this is a more useful form, that heat flows in which direction from higher temperature to lower temperature, and till when the heat energy flows from one body to another, till they achieve thermal equilibrium, that is, their temperatures become equal. So that is the one we'll be using more practically at the numerical level. Hope that is clear, beta. Yes, very good, beta. So next up we see the Fahrenheit scale of temperature. Right. So as I was saying, next up, let us look at the third commonly used. There are other scales of temperature also, but we will at our level be studying the three common ones, which are the standard international one, which is the absolute or Kelvin scale, then Celsius scale, which we saw, Celsius, or it is also called centigrade. They are one and the same thing. Okay. And the Fahrenheit scale. Okay. So in this, as you know, the boiling point of water is how much? It is 212 degrees Fahrenheit. And the melting point of ice is how much? It is 32 degrees Fahrenheit. So the difference of the two, melting point, boiling point minus melting point of water, the difference is of this thing, 180 degrees Fahrenheit. Okay. So a temperature difference of 180 degrees Fahrenheit equals to a temperature difference of 100 degrees C or 100 Kelvin. So this is what we use. So a temperature difference of 1 degree Fahrenheit equals to 100 by 18 or 5 by 9 degrees C or 5 by 9 kelvins. And therefore, similarly, a temperature difference of 1 degree C or 1 Kelvin equals a temperature difference of 9 by 5 degrees Fahrenheit. So you don't need to memorize it as 5 by 9, 9 by 5. You can just remember this simple thing, that these 2 points, let's say this is the melting point of water on any temperature scale, and boiling point of, melting point of ice and boiling point of water. Okay. So now when we look at the Celsius scale, this is 0 degrees C and this is 100 degrees C. So there are 100 equal divisions in between. Okay. Obviously I can't draw 100 divisions, but when I look at the same thing in the Fahrenheit scale, for example, then this same point of temperature is marked on that scale as 32. And this point of temperature is marked on that same scale as 212. So this temperature interval from here to here is 180 degrees Fahrenheit. Whereas the same temperature interval in degrees C is 100 degrees C. Or in Kelvin scale or the absolute scale. Yes, sir. Okay. So it is 100 Kelvin. Okay. So now let's understand the conversion. So X degrees C will become 32 plus X into 9/5 in degrees Fahrenheit. Whereas y degrees Fahrenheit will become 5/9 into y minus 32 in degrees. And then you understand the conversion between centigrade and Kelvin very easily, so it becomes like that. Okay, so let's see an example question. Convert a temperature of 122 degrees Fahrenheit to degrees C and kelvins. And second example, convert 25 degrees centigrade to degrees Fahrenheit and Kelvin scale. Very simple question. Yeah, I'll explain it to you. When we are doing this question, I'll explain. Because the 0 point is different. The melting point of ice is different. That's why you'll understand. You just look at this diagram, you'll understand why we have to subtract in this case and why we have to add from 32 in this case. It should be apparent from this diagram actually. That 0 on this is equivalent to 32 on this. Is equivalent to 273 on this. Okay, so just try this out. Yeah, anybody got the answer for the first one? Yes, very good. That's correct, Rupa. Yes, Archit, very good. That's correct. Now see, I will explain the question in a slightly different way. You can obviously use the formula and you'll get the answer. But I will explain the question like this. That in the first one, we are converting, how much was it? 122 degrees Fahrenheit, right? To degrees C. Okay. So think of the scales, then it will become very clear to you. So these are the three different temperature scales, let's say. Okay. So this is the Fahrenheit scale. So 32 degrees Fahrenheit. Okay. And 212 degrees Fahrenheit. This is the degrees C scale, let's say. So this is 0 degrees C. This is 100 degrees C. Okay. And Kelvin scale. So this is 273 Kelvin. Okay. 373 Kelvin. Notice in Kelvin, we don't attach the degree. Okay. There is some reason for that. I've forgotten. You can find out. It's a historical reason, something to do with the fact that he was Lord Kelvin and all that. Doesn't really matter, but I'm just telling you. Okay, so now see what is the temperature that we are given. It is 112 degrees, sorry, 122 degrees Fahrenheit. So that's lying somewhere here. Let's see. This is your 122 degrees Fahrenheit. So if you see this temperature difference, this is how much? This temperature difference is 122 minus 32, or it is a temperature difference of 90 degrees Fahrenheit. So now a temperature difference of 90 degrees Fahrenheit will be equal to how much in degrees C. So for that, you have to understand that a temperature difference of 100 degrees Fahrenheit, sorry, 180 degrees Fahrenheit is equivalent to a temperature difference on centigrade scale of 100 degrees C. Na? So therefore, so delta T of 180 degrees Fahrenheit is equivalent to the same in this much. Okay. So 1 degree Fahrenheit is 5/9 degrees C. So now use this. So temperature difference of 90 degrees Fahrenheit is equivalent to 90 into 5/9 degrees C. So it is 50 degrees C. So now wherever this temperature is on the centigrade scale, okay, this temperature difference, which is equal on the Fahrenheit scale to how much? To 90 Fahrenheit, is equivalent on the centigrade scale to how much? 50 degrees. So therefore this temperature should be how much? It should be 0 plus. So this temperature is some T degrees C. So T should be equal to 0 plus 50. That is 50 degrees. And likewise now on the Kelvin scale, this temperature will become 273 plus 50 Kelvin, or that is 343 Kelvin. Understood now? So this is the way you can visually understand the difference. This temperature difference will also be of 50 Kelvin, because 50 degrees C temperature difference is equal to 50 Kelvin. Okay, or you can just use the formula. The formula is always fine, that x degrees Fahrenheit will become x minus 32 into 5/18, sorry, 5/9, okay, in degrees. So just substitute. Okay. So likewise, you can also understand the second one. Second one in degrees C, I have given you how much? I'll just verify your answer. Just give me a moment. Yeah, 25 degrees C. No? just take the same diagram. Okay, so now my 25 degrees C is over here. So this temperature difference, so correspondingly, whatever it is in Fahrenheits, it should be here. So that this difference should be the same. So that delta T, which is 25 degrees C, will become 25 into 180 by 100, or 45 Kelvin. Okay, so T degrees Fahrenheit, okay, which is basically 25 degrees C, will become 32 plus delta T in degrees Fahrenheit. So it is 32 plus 45. So yes, correct. All of you got this correct. So 25 degrees C is equivalent to 77 degrees Fahrenheit. Sorry, this is not Kelvin, this is Fahrenheit. Okay. So the temperature difference above the melting point is 45 degrees Fahrenheit. So the exact temperature is the melting point plus that temperature difference. So 32 plus 45, 77. Okay. And of course, 25 degrees C is equal to 273 plus 25. That is 298 Kelvin. So that is this temperature here. Very simple thing, really, nothing difficult. Now let's come to the first effect of temperature or effect of heat on materials, and that is thermal expansion. So it is a matter of nomenclature that this section is called thermal expansion, but actually we study both the expansion and compression, both the things, contraction and expansion, according to whether we are increasing the temperature or decreasing the temperature. So typically any material, if you increase the temperature, the molecules tend to drift a bit further from each other. Now it's very difficult to understand why that should happen in the case of solids, because we think of solids like, as if the molecules are literally, pasted to each other or glued to each other. But at the molecular level, as I told you, it's not that way. There is some intermolecular space, there is some intermolecular bond, and the molecules are literally vibrating about those bonds. So when we increase the temperature, they vibrate a bit faster. So naturally the bond length increases. The distance between two molecules, and that distance being the bond length, that tends to increase as the temperature increases because they have more energy to vibrate now. Similarly, if we reduce the temperature, that vibrational energy is reducing, so they tend to come closer. So that is the effect. And obviously in the case of fluids, increasing the temperature results in the molecules moving about, in both translation and rotation faster. So more energy, more motion means that the physical size, the dimensions of the material will tend to expand when the temperatures increase. And similarly, vice versa, contract when the temperatures decrease. So that phenomena is called thermal expansion. So as I told you, it goes both ways. Okay, not only expansion with increase in temperature, but also contraction with reduction in temperature. So the expansion in the physical dimensions. So by the physical dimensions, we mean length, okay, surface area, okay, volume, whatever be the case as the physical dimension that we are describing. So the expansion in the physical dimensions of a material, okay, or a body, when its temperature is increased, okay, or vice versa of this contraction in the physical dimensions when temperature is reduced. This phenomena is called the thermal expansion slash contraction of matter. Okay. So you can say that this is a very basic thermal property of all matter. For all states of matter, all types of materials, all species, metals, non-metals, covalent, bond-based, organics, non-inorganic materials, organic materials, whatever be the case. Okay. Ionic bonded, materials, semiconductors, all materials known will behave in this way. Solid, liquid, gases, whatever, they will all behave in this way, that when the temperatures increase, their physical dimensions or size tends to expand, and vice versa. Okay, now there are certain physical laws associated with the thermal expansion, and they are mostly derived from experiment. So the laws of thermal expansion, you can think of these like experimentally determined laws. So the first in this is the principle of linear expansion. So linear means has to do with length. So the principle of linear expansion, or the law of linear expansion, is like this, that if we have any linear object or linear body, and by linear we mean that its length is much larger than its other dimensions, like a thin rod or a metallic wire or anything like that. So whenever we have basically a one-dimensional distribution of mass in a body, where the length dimension is much more significant compared to any other dimension. So for a linear body, example, a thin rod or cylinder, okay, or metallic wire is stretched out straight, okay, or any such thing, okay, the length varies with temperature such that this is the principle of linear expansion. The fractional change in length is directly proportional to the change in temperature. And the constant of proportionality is called alpha. It is called the coefficient of linear expansion. Okay. So delta L by L, this quantity, is called fractional change. That is the change in length divided by the original length. Fractional change in any quantity is nothing but the change divided by the original quantity. This is called fractional change. Okay. So anyway, and delta T is the change in temperature. Okay. So the law itself reads like this, that the fractional change in length of a linear material is directly proportional to the change in temperature. Okay. And the quantity alpha over here is just a physical constant for the proportionality. Okay. Yeah, so you can just note this down together. Okay. I'll scroll up, don't worry. So where the quantity alpha over here is a physical constant Okay, there is a constant of proportionality between the fractional change in length and this thing, and it is called coefficient of thermal expansion. Sorry, coefficient of linear thermal expansion. It is expressed in per degree C or per Kelvin. Yeah, delta L by Ln is only called the fractional change in length. Okay. Just explain. Delta of any quantity is change. So change divided by the original value is called the fractional change. And like if we say delta M by M, where M is mass, this is the fractional change in mass. Okay. Like that, delta L by L is the fractional change in length. So if we say that the original length was, let's say 50, let's say 50 centimeters. Okay, let's say the original length was 50 centimeters, then the length increased to 52 centimeters. Okay, so the change in length was of 2 centimeters. So now if I ask you what is the fractional change, so that fractional change will become delta L by L, or is a change of 2 centimeters where the original length was how much? It was 50 centimeters. So 2 by 50. So the fractional change is 0.04. Okay. Or you can multiply it by 100 and express it as a percentage change also. So 0.04 is the same thing as a 4% change. So that is the meaning of fractional change. Hope this is clear. You must have heard about fractional change in the chapter of errors and propagation of error also. Units, dimension and error, that chapter. Anyway, I'm just scrolling back to the page earlier. Some people have not noted down. Finish writing this down, then we'll come back to the principle of thermal expansion. Yeah, I'm scrolling down, people. So this is the principle of thermal expansion and the definition of coefficient of linear expansion. Okay, so just go through the definition of thermal expansion itself first. Then we'll come back to linear expansion. Okay, so alpha is a physical quantity which is called the coefficient of linear expansion, linear thermal expansion. Now, this is what we call a material property. That is, it is a physical property of the material of the body which it is made. So, for example, if you have a rod made of copper, it will have a coefficient of linear expansion alpha, which depends on the material copper. So another rod made of copper of different dimensions will have the same value of alpha because the material is the same. But if you make a second rod of same dimensions but of some other material like steel, it will have a different value of alpha. Okay, now let's understand the application of this. So also you can note down that metals have the value of alpha of order of magnitude 10 raised power minus 6 per degree C. So not sigma, alpha. Metals have the value of coefficient of linear expansion alpha, whose order of magnitude is typically 10 raised power minus 5 or minus 6, more typically 10 raised power minus 6 per degree C. Okay, so let's look at a typical example. A metallic pipe is of length L equal to 10.00 meters at a temperature of, let's say, 5 degrees C. Okay. If alpha for the metal is 2 into 10 raised power minus 6 per degree C for the metal of the pipe, then find its expansion delta L for a temperature rise of 30 degrees and its new length at a temperature of 45 degrees. In fact, let's make the question easier. Let's take this temperature change also as 40 degrees C. No, all metals don't have the same alpha. They'll have different values of alpha, but the order of magnitude will be 10 raised power minus 6. That's what I meant by saying order of magnitude. So for example, copper expands more than steel. So, if copper has thermal expansion coefficient of, let's say, 5 into 10 raised power minus 6, I'm saying, let's say, I don't remember the value. So steel will have less than 5, but that's something into 10 raised power minus 6. Now, order of magnitude, when we express something in scientific notation, we write it as a unit place quantity into 10 raised power something. So 10's power is the order of magnitude. Okay, so just work this out from the formula above. We'll discuss. Okay, so let's understand this. So what is happening here is that we will use the principle of thermal expansion, that delta L by L is equal to alpha into delta T. Okay. So for the first part, your original length is 10 meters exactly. Okay. Your coefficient of linear expansion is 2 into 10 raised power minus 6. And you are raising the temperature by a difference of 40 degrees C. Okay. So delta L will become L into alpha into delta T. So L is 10 meters, alpha is 2 into 10 raised power minus 6, and the change in temperature is 40. So that becomes 8 into 10 raised power minus 6 plus 1, that is minus 4. So the change in length is so many meters. So it is 0.0008 meters, or you can say it is that 8 into 10 raised power minus 1 millimeters, or it is 0.8 millimeters. So the length will expand by a factor of 0.8 millimeters when you raise the temperature by 40 degrees. नहीं, मैंने temperature 35 नहीं बोला बेटा. मैंने first part में क्या बोला है? The expansion delta L for a temperature rise of 40 degrees C. Understood now? How much it expands when I raise the temperature by 40 degrees. Okay, so actually the second part is the same as the first part. No, when I raise the temperature by this much, no, from T1, the final temperature T2. For the second part also, I want to find the new length. That is, new length kitna hoga? L plus delta L at a new temperature, which is 45 degrees C. Okay. Whereas the original temperature, the original length was L at T1 equal to 5 degrees. So it's the same question actually. Delta T is still 40 degrees. So delta T is 40 and L is 10 meters. Okay. And alpha is the same. So you have already calculated that delta L is 0.8 millimeters or 0.0008 meters. So my new length, so at T2 equal to 45 degrees C, the new length will be L plus delta L. So that is 10 plus, okay. So that will become this much. Yes, then the length contracts. So we will see how to service, that's correct. So we'll see how to change the formula so that we can find the length at a lower temperature also. Okay. So now we will also see that this formula that we have now, delta L by L is equal to alpha delta T. So according to this formula, if delta T is a positive change, okay, that is temperature is increasing, then accordingly delta L is also positive. So length increases. But on the other hand, if delta T is a negative quantity, that means the temperature is decreasing, then correspondingly delta L will also be negative. So that means the length will contract. Okay. So for example, the same thing, we had the length equal to 10.00 meters at a temperature of 5 degrees C, and our alpha was 4 into 10 raised by minus 6, or whatever, 2 into 10 raised by minus 6 per degree C. Now if I ask find its length at a temperature of, let us say, minus 45 degrees C. So that's a 50-degree change, but a negative 50-degree change. You understanding? So then what is happening? My delta T will be the final temperature minus the initial temperature. So that is going to be minus 45 minus of 5. So that's going to be minus 50-degree change. So delta L upon L is going to be a negative quantity, no? Okay. So my delta L here will become negative of 1 into 10 raised पर कितना हो जाएगा? 100 into 10, so minus 3 meters. Or it will contract by 1 millimeter. Okay. So as you go from this temperature to this temperature, this now means that the length contracts by 1 millimeter. Okay. So its length at this will become that will become the new length. Understood, Sarvesh, how we use it when the temperature is decreasing? Okay. So the same formula, the same concept only, that fractional change in length is directly proportional to the change in temperature. So अगर change in temperature negative हो रहा है, so fractional change is also negative. That means the length is contracting. Yes, density also changes. That's very correct. In fact, we will be seeing a formula later. You know, in fact, Sarvesh, you would have heard of the phenomenon of anomalous expansion of water. No? So generally what happens when the temperature of a material is reduced, its volume contracts, so the density should increase. But water has an anomalous nature that when you reduce the temperature from 4 degrees C to 0 degrees C, the density in fact decreases instead of increasing. Ice has a lower density than water because it floats. That happens because of a strange phenomenon of hydrogen bonding. So it behaves in an anomalous manner, but most materials, their density will increase as the temperature decreases. So take a solid block of wood or a solid block of any metal or anything like that. As you increase the temperature, the density will decrease. And as you lower the temperature, the density will increase. Vice versa. In fact, there will be a formula for that also. But before that, we will discuss about the surface expansion and volume expansion also. This is only the linear expansion. Okay. Now, the next principle we'll see in the thermal expansion concept is surface expansion. Okay. So if we have any surface, like for example, it could be the surface of a disk. So it has a surface area of pi r square, or a rectangular plate. It has a surface area of L into B, length into width, whatever. So any surface area, let's say A, also expands according to the principle that fractional change in area is proportional to the change in temperature, but the constant of proportionality is a different one, and it is called beta. So beta is called the coefficient of surface expansion. Okay, and this is also a material property. Okay, and incidentally, we will prove this later also. For any given material, the value of coefficient of surface expansion is how much? It is double of the coefficient of linear expansion. Don't think of it as alpha into alpha. It is 2 times alpha. The coefficient of surface expansion of any material will be double of the coefficient of linear expansion of the same material. Now, so if we know that, for example, some metal like bronze or something, some alloy like bronze has a value of alpha of 1.2 into 10 raised power minus 6, then its value of beta will just become double. It will become 2.4 into 10 raised power minus 6. So I will give you a proof of how this happens. Okay, it is actually based on a simple application of either you can show it from differential calculus or from binomial approximation. If you know the concept of fractional change, no, propagation of fractional error, you will understand why this happens. Yeah, Rahil, I will be giving you the proof of this later also, but for the moment, write it down as part of the definition. Okay, is it clear? Okay, let's look at a simple example. So we have a metallic plate like this. of length L and width D. So the metal has an alpha of 6 into 10 raised power minus 6 per degree C. Okay. And the length is equal to, let us say, 8 meters, and the width is equal to 5 meters at a temperature of 27 degrees. Okay. Now find the new length and width at a temperature of 77 degrees. From that, so what is the fractional change in length and fractional change in width for a change in temperature of 50 degrees C, which is the same as what you're doing here. Okay. Now calculate the fractional change in area from new values of length and width, and from that beta for that same metal should be equal to 2 times the alpha, or 1.2 into 10 raised power minus 5 per degree C. So we'll show that by numerical calculation. So just note this down. I'll tell you how to work this out. Okay. So let's see the calculation of each part. Okay. Now the original length was 8 meters. So delta L by L will be alpha into change in temperature. So that is how much? 50 into 6 into 10 raised power minus 6. So 3 into 10 raised power minus 4. That is my delta L by L. So the change in length will be equal to 8 into 3 into 10 raised power minus 4. So that is 2.4 millimeters. Okay. So the new length will become 8.00, sorry, 8.0024 meters. Okay. But now likewise, the width was 5 meters. So the fractional change in width will be alpha into delta T. This is also a linear dimension. It is a type of length only. It's the width, but it's a length dimension. Just like L is also a length dimension. Okay, so the same principle of linear expansion will apply to it. So the change in the width will be equal to 5 meters multiplied by alpha delta t. So 5 into again the same thing, 3 into 10 raised power minus 4. So that is 1.5 millimeters. The width expands by 1.5 millimeters. The length expands by 2.4 millimeters. The width expands by 1.5 millimeters. So the new width, the new length is this much, whereas the new width will become 5.0015 meters. So this is the answer to the first part. The new length and the new width will be this much. Okay. Now the second part, though, already you can see the fractional change in length is the same thing as the fractional change in the width, which is equal to alpha delta t, which is 3 into 10 raised power minus 4. Okay, so that's obvious. We've done this calculation here. Okay. Now the third part. See, the original area was how much? L into B. So it was 40 meters. The new area, that is how much? The new length into the new width. Okay. So that is 8.0024 multiplied by 5.0015. So I'll do this calculation using a calculator for you. So this meter square. But I will show you later by approximation methods also how to do this calculation without using a calculator. But currently I'm doing it for you using a calculator. Okay. I will, as I told you, I'll show you the method of binomial approximation also. So 8.0024 multiplied by 5.0015. ये हो जाएगा मेरा 40.024 meter square. This will be my A plus delta A. Okay. So from this now, I know that this was the original area. This is the new area. So my change in area delta A is how much? It is 0.0024 meters square. Therefore, fractional change in area is 0.0024 divided by original. So that is equal to how much now? So that will work out to be 6 into 10 raised power minus 4. Okay. So this is the fractional change in area. So this is the answer to the third part. Okay. Now you can see that this fractional change in area is supposed to be beta into change in temperature. So 6 into 10 raised power minus 4 is supposed to be beta into 50. So that means beta is how much? 1.2 into 10 raised power minus 5 per degree C. This is in degree C. Okay, so that means you can see that beta is twice of alpha. Is 2 into 6 into 10 raised power minus 6. So we are able to show that the value of beta for that metal is twice of the value of alpha. So here, as I told you, I've done it using a hard calculation, but there is an easy way to prove it that even without numerical values, every time the value of beta is not a coincidence that it's double of alpha. It has to be double of alpha because of the the nature of the fractional change, which is a very small change. Okay, so just make a note of this, people. Hope you understood this properly, and we'll conclude today's session here. I think we have another session coming up in a couple of days' time. So we will discuss further about thermal expansion, and then from there we will get into this thing, calorimetry, where we'll understand specific heat capacity, latent heat, and things like that. And eventually from the heat transfer. So that's it for today's session. People, wish you all the best. Yeah, delta A. What was the point, beta? Delta A's value is that much only, no? 0.0024. That's correct. Yeah, so Siddesh, how I got that? You're wondering that? Okay, I will just explain that. See, change in area निकालना है ना, final area निकाला मैंने, final area minus initial area है तो change in area हुआ ना. You understanding? Oh, sorry, this is 0.024. My mistake. Achha, that is what you were pointing out now. This should be 0.024, not 0.0024. Yes, okay now, na? Okay.